Hello everyone, welcome to the stream. We are here in SolidWorks with a PB560 ventilator, which we're going to be looking over today. How's everyone doing tonight? Get the chat up, which seems useful. Seems like we have a nice number of people here. Let's see, we've got Chan, Raul, Hernandez, welcome back, Hernandez, Yukon, welcome. Ian, nice to see you again. Nathan, welcome. Doc, nice to see you again. Lots of familiar names in the chat. Okay. Let's see. So, as I'm sure the entire world knows by now, there's a bit of a pandemic on, and this pandemic can cause respiratory distress in a limited number of cases, particularly people that have comorbidities. That would be things like prior respiratory issues, scar tissues, obesity, advanced age, a variety of things like that can increase your susceptibility to the disease. So the trick is that fascinating. Okay, so the trick is that these people may require respiratory support in the form of a ventilator. And there's right now a lot of speculation that possibly there will not be as many ventilators as required to handle the peak caseload when COVID-19 cases reach their maximum in late April, early May. So there are a lot of people that are thinking about how to build more ventilators. And the secret is that ventilators are not a really great candidate for hobbyists to hack. They're complicated machines with tight requirements, and while the FAA has given guidance for how to get emergency ventilators certified as medical devices, there are still associated complications. So if you're looking for ways you can help with your own fabrication expertise, you should definitely be looking at things like making PPE, face masks. Joseph Prusa has published a 3D printable model for face masks that can be printed by you at home, and there's a lot of doctor demand for that. If you can sew, sewing masks is absolutely one of the most useful things you can do right now. So if you have a sewing machine so you can make parachutes for your rockets, you can definitely repurpose that. But there are still some people working on open source ventilators. There's the open source ventilator movement. There's OpenLung. There's MIT's eVent. There's a large variety of these emergency ventilators being stood up. And the secret is that all of them are just less good than what we have right here. This is a relatively simple ventilator. It's a continuous positive pressure type ventilator. Some people incorrectly believe that these machines are not what are referred to as ventilators, but the true fact is that it's a that classification refers to the outlet pressure and how it's cycled, not whether or not you can use a CPAP machine to treat COVID-19 cases. So that's where we are. To help other manufacturers that may have spare capability, to help hobbyists that might be tinkering, Medtronic has incredibly graciously released the design files for this ventilator design, which we're going to be looking over today to see if there's any insights we can glean from it, any parts we can make, any support that can be offered. I don't know if we'll find anything useful, but I thought it would be interesting to look over. So that's what we're going to be doing. Okay, and with that, let's see. Oh, we've got more people in the chat. Welcome, AstroFox. Welcome, Brandon. Kempvik, welcome. Sleeve Dog, Eric, Alan. Thank you for joining us. Okay, so cosmic exploration. For making masks, you can use just about anything. Your goal is to trap droplets that may contain virus particles suspended in a fluid. So you want a lot of surface area. It's also helpful if the material is slightly charged. So like polyethylene is a good idea. Okay, but let's start breaking down what we've got here. So this device here, we've got We've got the control interface here. It's got battery warnings. It's got, I think that's signal. Um, I guess that would be for an information button. But this is not a component that our emergency ventilator would have. We don't need that fancy of a GUI, so we'll just go ahead and hide it. Mostly this is just going to be like hiding components to see what we've got. So that was the entire upper housing of the assembly, and we'll go ahead and do the same for the lower assembly. Okay. So this appears to be a plug for an alarm, maybe to connect to an existing hospital information system. This is going to be power right here, as well as a DC 12-volt jack. And those appear to be other interfaces and maybe a USB port. So I would guess that this right here is probably the main electronics. And then a little covered power switch. That's a really good idea to make sure that it can't be inadvertently turned off. You need to open the switch and hold it open since it's spring-loaded in order to be able to access the power switch. So this is going to be the main electronics, it looks like. And then there's a ribbon cable that runs the display. If I had to guess, I would say that these three devices right here are barometric pressure sensors. There's a little bit of a language barrier here. My French is not particularly excellent, and a lot of these components are annotated in French. This is going to be hooked up with flexible plastic tubing to this line right here, which I believe goes to a air pressure source, and this whole device just regulates the flow of pressure to the patient. So let's see. So that's that. So let's go ahead and see what we can do about hiding the control electronics, because we won't be doing anything with those. This PCB there. There we go. Okay. Ah, fascinating. Okay, so then here are two components on the underside as well. Okay, returning to the chat briefly. Yes, I'm very glad to hear that people are printing face shields. That's like one of the most useful things you can be doing. The doctors really need the PPE right now. The medical system will be under even more stress if we don't keep the doctors healthy. Nathan, I do have the most recent files released today. Okay, so what I believe we're looking at here is, I think this is going to be more of the pressure transducers in this little housing right here, just like up here. And then this is more clear flexible hosing, and I think these might be valves. Let's see if we can figure out what these components are here. Okay. So to some extent, this is not functional CAD. This is like bounding box CAD, which is unfortunate. But I think these are going to be valves. And so if I were to speculate on their purpose, it looks like there are connectors here. This is the effluent tube, and this appears to be where the lungs attach. So this would go to a filter to scrub virus particles. And this here would go to the pressure source, and this appears to go to instrumentation. These devices here are, I think they're electrical buzzers that connect up to the control electronics to give additional audible warnings. If the machine becomes disconnected or if the patient is having a serious breathing issue. All right, so that's that. This is more of the housing, so we can go ahead and hide that. This just appears to be a structural component. This is a handle, so you can get your fingers under here and lift it, and it appears that it hinges there. So we can go ahead and hide that as well. All right. So now let's figure out what we're looking at here. So probably the next thing we want to find and hide is the power supply, because that's just going to be kind of whatever you need to make this work. So I think that is this component here. Nope, this is the battery. Okay. So the battery is a requirement because this medical device has to operate if the power goes out because it's life support critical. And it looks like the battery is even replaceable. If you undo the screw right here, it looks like you can just drop the whole battery compartment, which is really clever in case you need to swap batteries to keep it running or maybe change batteries when maintenance is necessary. So that's that. So this appears to be another PCB that connects the faceplate of the battery up to the rest of the electronics. So if I were to guess, oh yeah, look, those are spring-loaded contacts right there that connect the battery up to the rest of the electronics. And the reason I know exactly what a spring-loaded contact looks like in CAD right now is because I'm using spring-loaded contacts in another part I'm designing. I'm shamelessly abusing them. They're supposed to be for electronic signals, and I'm using them as pins to retain a telescoping actuator. So these little widgets, I assume, are just to help retain the battery in the right location. Okay, so here's what we've got. So this is the O2 line. So this is how you supply enriched air to the patient. So it's got a twist to connect feature. So you push it on, it depresses that pin, you rotate it, and it locks in place. And then you've got this clear plastic hosing with a kind of a swageless fitting there, and that runs into this apparatus here. All right, this apparatus has 2 wires and 2 ports, which make me think that this is a metering valve. Yeah, okay, so I would guess that this right here is a metering valve to allow you to dynamically change the oxygen enrichment. Zach, thanks for the tip. I'm going to look at the assembly instructions right after I'm done looking at the CAD. Just fighting with the model a little bit will help me have some recollection of what everything does. So then this tube comes out of the oxygen adjustment valve and into this apparatus here. Ah, okay, so this is not provided with positive pressure air. I think this is the pressure system here, and this is just an intake, so you can intake from somewhere with clean air. Let's see if we can validate that hypothesis. This is the air fan. Okay, cool. So this is something that 3D printed machines do not do often. So most of the 3D printed machines that I have seen are of the, let's see, the Nautilus gear style. So this is one that I've been working on, where it's got a stepper motor that can control the position of a Nautilus gear to depress a ambu bag. And I think that's a really good way to do it with the limitations that amateurs have, but I think this is even better. Because if you can have valves, then you can just always be generating the pressure you need and then just open and close a valve, and the valve timing determines the tidal volume of air. So the tidal volume is the amount of air that goes into the lungs. And so then by adjusting the valve timing, you can control the tidal volume without having to mechanically adjust things. And then also what you can do is you can adjust the pressure delivered by air by controlling the speed of this blower. And you only need you don't even need like a half PSI of air. So I think this is actually a really good way to do it that I think more people should be looking into. I've bought some high-powered drone motors to try and rig our own CPAP machine. That seems like a good way to try and do this. Okay, so that's what I think this is. I think this right here is a I think this right here provides the air pressure. So working under that assumption, this would be the air inlet here. And then we've got the inlet here. This tube right here is what provides the enriched air. So that would make, let's see, so what do we got? Then we've got this tube here. This tube runs up to this line right here, which goes into this widget here. So I think this is control feedback for, no, this is going to be another solenoid. Yeah, this is another solenoid. Because you see it's got the wires coming out of it. So this is, oh, and there's the coil right there. Okay, so this is a solenoid valve right here. And it looks like it has NC and NO ports. So this is going to be the outlet. This would be the normally closed inlet, and this would be the normally open inlet. I think that's how that works probably. So then, or maybe I've got the reverse of that, but something like that. One of these will be the normally closed, one of these will be the normally open, and then this will be the outlet. So then it takes the outlet and it goes to this splitter here. And this splitter provides one pressure to a sensor on the control board, and the other one comes to here. Ah, okay, so my working theory of this is kind of falling apart. I'm trying to like imagine a PID in my head as we work through this. So let's see, I think this still strikes me as where it does where you hook up the intubation equipment. So that means that I think this is an outlet tube, which means that this is an outlet tube. Maybe it's a differential pressure sensor, and these aren't valves, because if this is a valve here, okay, so if it's not that one, maybe it's this one down here. So that one goes into this valve here, and this line here connects. Okay, that's weird. That looks like it just goes in a loop. That does not make sense to me. What's going on in this part? Let's change the transparency on it. So it looks like this is a plastic backing to this injection molded piece. Interesting. Okay, so both of these tubes, let's see what's happening in this one. Change the transparency. Okay, so okay, here we go. This is starting to make a little sense. So I think this is the outlet tube, and these are pressure sensors on the outlet tube, one of which is a differential pressure sensor with the high pressure air, one of which is a differential pressure sensor for calibration. Okay, that's making some sense. So these are not actually, these are delta P barometers right here, not valves, which makes this still the only valve we know about, which makes this device here the pressure generator, which makes this the connection to the human here. This is where your intubation equipment would go. Ah, and then this is the filter media right here. Yep, entrance filter, and then this is the inlet for the continuous positive pressure generator. Okay, so starting to make sense. Let me look at the chat, which I've kind of been ignoring. Let's see. Yes, I have the newest files released today. The assembly instructions. We should check those next. Braden, I don't know if that is where the air goes along. I'm pretty convinced that this is the outlet here, that the air comes from here, and then you breathe out through this tube here, and there's like a vent there. That seems to be what makes the most sense to me now. All right. So with that in mind, I think we kind of now have an idea of what all the widgets on this do. Big capacitor, power supply here. This will be the motor driver right here. Uh, yeah, okay. I think that's really getting like all the details sussed out. That's some beautiful harnessing there. I should really spend more time modeling harnesses on some of my parts. Okay, so we've really got this deconstructed, and that's kind of what we need to know. So the next thing we should look at is the assembly instructions, which were suggested as good reading. Let's see. So that's the mechanical part drawings, manufacturing fixtures, electronic PCB assemblies. J-Hines, it's not that one's for calibration, it's that you're measuring different delta P's, and they give you different pieces of information. So you're using one, so this one right here is the offset between this tube and this tube here. Right? So you're measuring the difference between this one and this one. And so if I had to guess, that's like a pitot tube essentially, right? So to cancel out the effect of velocity, because you've got this one here. So this one will see the total pressure because it's kind of ram air inflated. And then you've got this tube right here, which is going to measure the static pressure. So this is just like the pitot tube on an aircraft, where you've got one thing measuring the ram air pressure and one thing measuring the static pressure. And then this delta P sensor up here is measuring the difference between the pressure to the lungs, which is this tube here, pressure in the lung, and this tube. Oh, weird. Oh, I bet this is like another pitot tube assembly, right? So I bet we'll find that one is facing that tube and one is orthogonal to the tube, right? So there's the orthogonal one. Oh no, that's weird. Look, they're both orthogonal to the direction of flow. That's weird. So why are they measuring the delta P across this? They're measuring the delta P across this screen. Why are they measuring the delta P across the screen? Also, that connector isn't wired up to anything. I wonder if that's supposed to... Oh, I bet the wires are a part of the PCB, which I hid. That would make sense. Okay. Weird. So they're measuring the delta P across this screen. Can anybody think why we do that? Maybe the screen causes like a known pressure drop? I do not know. I do not know why it would do that. Okay, so with that in mind, we now know what the pressure sensors are for. We now know what the valve is for. We know that's where the outlet is. Okay. It's making sense. We're pulling it together. We're coalescing an idea of what's going on here. So, let's see. We want the assembly instructions. So, I think that's going to be in the first data release. Let me do this not on the stream. That seems like a wise decision to not live stream my entire computer file structure. All right, service manual. Let's see what we got going on here. All right, can I get 2 pages? Yes, I can. This is thrilling. Okay, let's see. We want some variety of mechanical general information, theory of operations. You know what? Let's be thorough. Let's read the whole thing. Sorry, folks. This is going to be not the most interesting as you just listen to me read stuff, but I promise I will read quickly. Okay. Um, oh, Nathan, thank you. I would love to find the plumbing diagram. As anyone who's been on stream with me before knows, Dr. Pepper is absolutely essential to my functioning, which is bad. It's unhealthy, and I should kick my Dr. Pepper compulsion. But a pandemic is the wrong time to quit drinking soda. Um, okay. Pneumatic operating ranges. Uh, SCCMs. So it's measuring -10 to +100 centimeters of water. So that's like minus a tenth of a psi to +1 psi, give or take a little bit. That's about what that is. Uh, the oxygen valve takes 7 psi at 15 pounds per minute. That'll be probably pretty standard for a hospital. It's got a turbine. Wow. Okay, so this is turbine-driven air pressure. Uh, let's see. So at 50,000 RPM, it can do 240 liters per minute. Holy cow, that's a real turbine. I mean, that's a nice turbine. Okay. It's got a checking oxygen inlet valve. It's got an oxygen solenoid valve. Okay, so that wasn't a throttle valve. That's just a solenoid valve. It's a normally closed 24-volt DC two-way valve. It's funny because I've got like a whole pile of these things sitting on my shelf behind me. Yeah, it's essentially one of these. Okay. Let's see, the inlet silencer, there's a turbine assembly. An inlet silencer removes noise from the air inlet side of the turbine. I guess that's like an important quality of life feature. It would really suck to be stuck in a hospital and all you could hear is these like things everywhere. Outlet silencer, exhaust, exhalation solenoid valve. The exhalation solenoid valve is an electromagnetic three-way proportional valve. Oh, okay, so I was right. It is a three-way valve. Pressure supplied from a port at the turbine connects to solenoid valve 1. Solenoid valve port 2, pressure through the exhalation valve port on the inspiratory block to the patient circuit exhalation valve diagram, where the patient is... All right, let's check figure 3A. That's what we're going to do. Okay. So external power, mains power, internal battery, PCB connection, communication system with some USB ports, system interfaces, microcontroller fan, voltage regulator. Okay, this is just power management. Exhalation solenoid valve during inspiration and exhalation. Okay. So port 3 vents to atmosphere. So if we go back to the CAD and we're looking here, this is going to be port 3 right here. It vents to atmosphere. Is there any labeling on it? No, it doesn't look like there's any labeling on it. Okay, so that's port 3. That's going to vent to atmosphere. Port 2 connects to the patient circuit exhalation valve and exhalation pressure transducer. And port 1 is turbine flow. So if we go back to SolidWorks, turbine flow is this one right here. So this is port 1. That's port 2, and that connects to the exhalation pressure sensor, which we know because that connects to this one right here. So this is going to be the exhalation pressure sensor. So this tube right here is the exhalation pressure sensor port. That one right there. Okay, reading the chat because there are a bunch of smart people in the chat who have been very helpful already. Okay. The orthogonal hole is just a friction surface for a sensor that is not subject to the velocity pressure? I don't know. I don't think so. Probably not. The requirements doc has a plumbing diagram in it. Yes, we're looking at that. You only need 10 liters per minute max. JK, it's like 6 liters per minute max. So Braden, the thing is that you have to remember the duty cycle, right? So because this is continuous positive pressure, it can do 580 liters per minute, but if you take 12 breaths a minute, that's like a fifth of a cycle. So that means that it's only producing 100 liters a minute. And probably as back pressure increases, the flow rate decreases, would be my guess. I don't know that as a fact, but that would be my suspicion. What's everyone else doing tonight as I look over all kinds of weird streaming documentation? Let's see. Okay, so back to the documentation. Ian, could you modify a vacuum cleaner, put an air filter in it, put the output to the lungs, but vent it so it's not such a high PSI? Ian, the one thing you never, ever, ever want to do on lungs is pull negative pressure. If you ever pull negative pressure on the alveoli, the little sacs that make up the lung tissue, you'll collapse them and bad things will happen. So don't ever pull vacuum. In fact, a lot of ventilator machines will actually have the patient exhaling against positive pressure. So you don't ever want to pull a vacuum on the lungs. Like a tenth of a PSI would be like catastrophic. So you always want there to be positive pressure. Let's see. Pneumatic block diagram. This is where I should have started right here. Let's see if we can zoom in on this. Okay, so we've got 3, which is the turbine. 4 is what we think is the exhalation solenoid valve, which we agree with. All right, and that's wired up exactly the way we think it is. So this is going to be the exhalation pressure transducer. 5. Yep, that's right. So then this DP sensor here is 7. What is that? That's the inspiratory flow sensor. Okay, so whoever was thinking that's a flow sensor is right. So there's probably some known pressure drop over this grating. And then by knowing the pressure upstream and downstream, they can get the volumetric flow rate. Okay, that makes sense. So just some ideal gas law type stuff. This block right here is 13, which is the inspiratory pressure sensor. So I bet this is how they're triggering a breath, is when the pressure on this falls, they are delivering a breath. 14. So 14 connects here. No, so 13 is not connected to the patient. 13 is upstream of the patient's breath. So sensor 13 is just measuring the pressure in this and probably regulating that. So sensor 14 is connected to the mask on the patient's side downstream of the check valve. So sensor 14 could see a negative pressure. So 14 is probably what they're using to trigger the breath. 8 is a bacteria filter. 9 is humidifier, nebulizer, or additional water trap. So 9 just makes the air comfortable to breathe. 11 is the proximal pressure tube. Okay, yeah, that makes sense like we thought. 12, patient Y. Okay, I'm guessing that's just like a phonetic version of the word Y. Let's see. Back to the chat. Jay Hines, I am envious of your alcohol this evening. I am attempting to remain sober, so I have some technical competence to learn new things. I'm not a medical person by trade, so this is requiring some of my mental faculties. Other people are comparing their favorite recreational substances. Hernandez, why are you watching 2 streams? Go watch whoever's being fun and entertaining. I'm just reading off a sheet of paper. Let's see. Nuffly, learning about mechanical ventilation 2. There's a far simpler challenge by Columbia University in New York. Yes, Nuffly, you actually are the second person to tell you about this today. One of the other people at the company I'm at right now just told me about that. I think he's preparing an entry. Just for the record, my primary idea is to do actuated ambu bags with cams. It's much simpler. But what I really wanted to see was how the professional units do it, so I could see if there was something I wasn't doing that I should have been doing, or maybe this turned out to be super easy. I'm still actually not sure. Just because I haven't seen anyone else try it, I think it might be worth trying to set up a continuous pressure turbine. That seems like something worth trying, just because no one else is trying it. Let's see. Let's see. Do I plan on recreating the ventilator trio? Probably not. I don't think I have the capability to reproduce most of this. Certainly not on a useful time frame. But I'm hoping I can steal some good ideas from it. Let's see. That catches me up on the chat. Back to reading here. So that's the circuit to the patient's lungs, and then 18 is the expiratory tube. 19 and 20. What is 19 and 20? It's a water trap. Okay, so they don't want any water getting into those ports that we just were looking at. What's 22? 22 is an exhalation valve, and 21 is the exhalation block. 17 is the exhalation flow sensor. Okay, we got that. Yep, we decided on that already. That's cool. 36, low pressure O2 inlet. Yeah, we had that. And then 37 is the O2 solenoid valve, which we also found. Okay, cool. So I think we reverse engineered everything on the main unit. So this was a super good find. So Braden, it's important to note that that continuous air pressure turbine is how the professional device works. It is the kind of the hacker movement that isn't trying it. And I mean, especially given how prevalent quadcopter motors are, it seems like something worth trying. I mean, it seems like you should be able to print the volute and the impeller and spin it up with a quad motor and generate positive pressure that way. I don't know how well it will work, but certainly there are a lot of other people that have developed very effective ambu bag actuation systems that are not me. I don't think we need another. I mean, I'll keep working on this one here, but I don't think we need another person working on that, right? Like, kind of the fact of the matter is that no matter how good I am at what I do, I'm not going to be the best person building an ambu bag respirator. I don't have large manufacturing facilities. I'm a team of very few people. So I think the key is that I should be looking to mitigate other possible failure modes. Okay. Let's see. Kevin, you're wearing a hazmat suit and using an ambu bag. If I were to try and build something, I might do more harm than good. Yeah, Kevin, we really have to be careful about that. There's a significant risk to doing more harm than good here, and I think we all need to be aware that like a DIY ventilator is going to be a very hazardous machine and should only be used with appropriate medical supervision, even if you built it right, because as patients get sicker and sicker, their respiratory requirements change. A healthy patient may only need like 12 breaths per minute of like approximately 400 milliliters of tidal volume, but a sick patient may be respirating 32 times per minute with much lower tidal volumes, 120, 180 milliliters of tidal volume. So really, even if we build a working system, we then need a doctor to help us operate it correctly. Okay, Ethan. Oh, hey, Ethan. Welcome to the stream. I haven't seen you around here before. EDF, not quad motor. Ethan, that's a great idea, except I'm a few EDFs short of a ventilator. I actually don't have any EDFs behind me. I do have a couple of quad motors. I also have, Ethan, you'll get a hoot out of this. This is my main propellant valve for my 6 kilonewton liquid engine. Ethan Perrin is an absolutely brilliant aerospace and mechanical engineer as well, and he has also liquid engine experience. Jay Hines, don't hospitals have house pressure lines? So Jay Hines, there's a lot of requirements for adjustability on the ventilator side, and so this machine is able to provide if you think about it. uh, this is only a single one of the components in this machine. So if you wanted to replace it, you would want to, if you wanted to just use the hospital air, all you do is replace this component, and you'd still have, the air, the oxygen solenoid. You'd have all this pressure sensing equipment. So really, I think there's not too much to be gained by replacing that unit. Also, because that assumes that your patient is in a hospital, and I think especially as the situation devolves, the possibility of a patient being in a field hospital goes up, which may not have the same infrastructure as a real hospital. Uh, Spirit, yes, you're right. It does add components to make a turbine-based system, but not all that many, right? Because for the ambu bag system, you've already got cams and motors and stuff. So I think the trick is just being cognizant of the manufacturing complexity. Um, but Spirit, it also doesn't all have to be medically safe because all those components can be upstream of the filters. I mean, it obviously can't, be harmful, but I don't think it all needs to be sterilizable. Um, uh, yeah, Jay Hines, these components in the Medtronics one aren't stainless steel either. Certainly, they can survive an IPA wipe, though. Okay. Daniel, is it possible to use off-the-shelf scuba diving compressor to maintain a constant positive pressure instead of a turbine? Daniel, your problem there is you have to reg it way the heck down, right? Your scuba tank outputs at 3,500 psi, depending on what tank architecture you use. And so when you're breathing through a scuba mask, you need a first stage to drop the pressure, and then a low pressure second stage regulator in your mouth. Um, I don't think the problem is generating the pressure. I think the problem is having enough controllability to safely deliver a breath to the patient. Uh, Nuffly, there are actual clinicians and engineers reviewing these submissions. Yeah, definitely. And I'm working with a pulmonologist as well as a team of other people on my solution as well. I'm not just throwing mine out into the void. Uh, Kevin Stewart, I like the idea where I read about the Italian doctor making one ventilator able to be used on 4 patients. So Kevin, the danger there is that you could damage other patients if they're have different pressure requirements. So they've been really hesitant to encourage doing that until we start running out of ventilators. And even when you're doing that, that's kind of like a last-ditch effort. Um, let's see. Nathan, I think it's important to remember that the virus is not the only major hazard. When you're intubating a patient using this apparatus, you're like drastically increasing the risk of secondary infections. So while the virus is bad, the patient already has it. And the next patient going on the emergency ventilator probably also has the virus. So you're worried about secondary infections as well. Um, Okay, so that is that. Let's see what else we can glean from the uh, book here. This is the turbine assembly drawing. Who makes the turbine assembly? Let's find that out. Is this a component we can buy? Manufacturing documents. Nope, doesn't have anything there. Requiring documents. Okay, this is a useful document for designing your own, and getting it FDA certified, but this is not what we need right now. What we need right now are let's see, we need oh, what do we need? Mechanical part drawing. So this part number is VEN 10226A. Then 10226A. There's not a part number labeled 10226A. But there is a part 100-287-68. 100-287-68. Let's see. I'm just going to start opening pictures. So this is going to be the bottom housing. So this looks like it's probably injection molded. It's, let's see, applicable standards. So this calls out how you should interpret the drawing. Dimensions are in millimeters. Material used. Does it call out a material? No, it does not call out a material. Certificate of compliance required. Okay. So we don't need that one. What's this one? This is going to be the top housing, I think? No, this is a harness. And it's all in French. Alarm repeater harness. So this is that connector on the back that talks to the rest of the hospital's alarm system. A Norden Fluid Control Company. Oh, this is going to be one of the solenoids, I bet. Yeah, here we go. So this is the three-way solenoid. So this is the exhalation pressure control solenoid. Port 1, port 2, port 3. No drawing notes. 540 ohm, 31 milliamps. Okay. Cool. What else do we have? Ooh, this one's zipped. Why is this one zipped? What is this? Outer shipping carton. Oh, this is how it ships. Okay, that's not helpful. That's like the opposite of helpful. And this is the parts that make up the thing that ships it. Okay, well, if we need to ship it really well, now we know how to do that. A fan? Wow, we are deep in the high medical tech regime here with that fan. Blank label. This is a label. All right, well, we can put labels on our things now. I swear I was in the right folder to get the turbine. Okay, this is a useful part. It's not what I was looking for, but it's still useful. Let's see. Sleeve dog, I am a fan of using whichever measurement system is the best suited to my needs at the time. So for example, when I'm doing calculations, I will almost always do them in metric just so I get the units right. Dimensional analysis is a lot easier in metric. But if I were, for example, going to manufacture something, I would almost always work in imperial because my shop is set up for imperial, as are most aerospace shops. Okay. Nathan, do you know what the number on that drawing is so I can find it as well? Let's see. Support with conic fittings. These are going to be the inhalation and exhalation ports on the edge of the machine. So these are the molded fittings. So let's see, it calls out all the dimension, it calls all the drawing specs, dimensions in millimeters, ABS, polyacrylic, PA, colored, okay. No texturing of the part. Refer to the 3D model for dimensions, geometry, surfaces, and features not shown or dimensioned on drawing. That's pretty standard. At SpaceX, we called this the magic note because it lets you be really lazy making the rest of the drawing. Um, okay, this is a cool part, but still not the one I need. This is a piece of foam, an electric filter with foam rebranded. Okay. What else is in here? More filter stuff. Yeah, this is all filter stuff. Okay. Nathan, electronic PCBA's blower driver PCBA. Is that the? I thought that'd be the spec for the driver board for the turbine, not the turbine itself, Nathan. Do you have any insight? Let's see, 196, 315. Do I have one for that? 100. Um, let's see. I think I can. I think I can show this now. I was trying to hide what all my file structures were on my computer, um, which seems wise. Electronic PCBAs, blower driver, turbine control box specification. Okay, here we go. This is promising. So this is made from aluminum, and the front is molded from ABS plastic. Gas sources. The turbine enclosure shall contain an air inlet and an oxygen inlet, which it does. The blower shall meet its performance requirements at 5 to 40 C with humidities between 10 and 95% relative humidity and barometric pressure from 600 to 1100 pascals. So that's like half a psi to 1 psi. Weight. It weighs like 2.5 pounds. Labeling and traceability. And lot number and or serial number. So it doesn't say whether these are serial or lot tracked. Okay, so it's looks like it's essentially just like a like a three winding motor with Hall sensors, so it's got speed control feedback. I mean, this is just like a BLDC motor. This doesn't tell me anything about the turbine though, unfortunately, which is what I'm really interested in. This is the control board. Nope, nothing really interesting there. Okay, let's see. Where else could this be? Maybe they have a 3D model of it? Ah, they do. Okay, so this is a higher fidelity 3D model. So if we extract it here, let's see what this opens up as. Which of these is the assembly? There are 3 assemblies. I guess when in doubt, we open the biggest one. That seems promising. No, this looks like the driver board, not the turbine, which is unfortunate. So that's that component there. I bet if we change the transparency on this, yeah, that's unfortunate. It doesn't have anything inside of it. It just is, they modeled the box. Ah, that's frustrating. I mean, I'm very grateful they decided to share as much as they have. I just wish they would have included that. Mechanical part drawings, we kind of already looked through that. Manufacturing fixtures. They've got tube cutters, harness making stuff. Battery fixture? Huh, interesting stuff. Okay. I'm going to discontinue my quest for the Holy Turbine and continue scrolling through the user's manual. Oh, here it is. Turbine. Does it give a supplier for the turbine? Is this a thing that exists that I can like search for? 268 turbine. Google does not immediately tell me that there's a turbine that is easily available with that part number. Okay. Kevin Stewart with a random question. You read that Ford has made mechanical devices before. What would make an assembly line for a machine this look like if made by Ford or Tesla? So Kevin, as far as I can tell, there's a lot of injection molded parts on this. So they would machine a die, a tool, to pull the parts off of for all the plastic parts. And then they get vendors for the solenoids, or maybe they'd build a machine to make the solenoids, but probably I bet they'd get a vendor for them. Those are just going to be a bunch of machined parts with tight tolerances. And then the turbine would, similarly be something assembled. So my guess would be that they would start with the base fixture. They'd put the battery in. They'd put the turbine in. They'd put the power supply PCB in on top of the battery. They'd add the control electronics, and then this tube is all flexible. You don't even have to bend it, so you can just, route this all by hand. And then they'd probably have a test machine to make sure it works, and then they just put together the next set of parts. Let's see. Oh, Nathan, that's cool. I mean, it's not necessary. I mean, I won't be able to do anything particularly useful with that information, even if I had it. I'm just kind of trying to figure out here. Like, I've already gotten some really great insights here. Like, I knew there were really tight tolerances for the pressure measurements. That like the patient is very sensitive to those, and the DP sensor is a brilliant, brilliant idea. And I knew about DP sensors. I've used DP sensors before to measure LOX levels in tanks. And I just didn't even think of using them in this device. I wonder, let's see. Let's see if what are the options for DP sensors, for like hobby level DP sensors? Well, DigiKey has it, so that means that it can't be all that esoteric. What's the spec on this sheet say? Hey, Nicola, welcome to the stream. Thank you for joining us. Jay Hines, do you know or have any open source turbine models, CAD, or drawings? Yes, Jay Hines, I actually do. It is not that difficult to do turbines, and one of the liquid rocket engine videos I have scheduled to go up eventually when I finish editing it is a video on electric pumps. So I have a 3D printable electric pump for water just to demonstrate concepts. It doesn't, produce rocket engine useful pressure levels, but it is just kind of a little project. Let's see. Ethan. Honeywell is always an excellent supplier. I wonder what they cost. This is $16, which is really not that cheap to start with. 2.5% error with auto zero. What's the pressure range on this? Pressure range. Minus 2 kilopascals to 2 kilopascals. So that's like 1/50th of 14.7 psi. Accuracy. Maximum pressure, 75 kilopascals. It's going to be kPa gauge. No, that's going to be delta. So that's going to be like 10 psi. So we could definitely use something like this. this is absolutely something that we could use. That's good. That makes life a little easier. J-Hines, there's definitely some downloadable CAD models like on Thingiverse and stuff. I think I had a friend of mine in an additive manufacturing class that 3D printed a water turbine that ran on a little motor. I don't know. He might have modeled it himself, but it's really not that hard. Making a good one, that's hard. Making something that works isn't that hard. Um, all right. Well, this is where we are here. I don't know what more there is to glean. Um, yeah, I think it's pretty straightforward. Oh, excuse me. Yeah, so there's, the requisite sensing systems, the high fidelity delta P sensors, the flow rate idea by having that grate with the pressure drop, um, turbine outlet. Uh, we have no particular information on this turbine, which is unfortunate. Um, uh, Nicolo, I do. I'd love to put my rocket engine on a rocket. The hairy part there is that I have yet to even static fire the engine, so designing a rocket now would be premature. I want it working first. Um, and I need it working very well, because the rocket will be, like a flying test stand. The test stand's several $1,000s, so uh, that makes it seem like the rocket could very easily be very, very expensive. Um, For now, I'll be happy just working on the test stand. I got like an 80-pound sheet of steel in today for a monopropellant test stand that I'm working on. We'll see how that turns out. That's, I think, a Patreon's only project for now. Um, but I'll hopefully one day use it as the igniter on my big rocket engine, as this little monopropellant igniter. That way I can do relights. Okay, Adam, do you know if this design is representative of most ventilators in the field? Adam, this design is actually a relatively low-end design from the field. It's kind of like limited in capability and feature set, but Medtronic said they chose to release this one because they think it is the one that it would be most feasible to scale up manufacture of in a short period of time, which I kind of don't disagree with. This looks like a very, dare I say it, straightforward piece of kit. It's like what, 4 PCBs, a power supply, 2 solenoid valves, 2 DP sensors, 3P sensors, and this turbine assembly, which appears to be the most complicated part. So I can definitely see how this is something you could like rush out. So for example, this giant battery pack we hid that fills this corner down here, Tesla probably makes, 20 of those per car. So it definitely seems like something they could help with. Let's see. Jay Hines, you've worked on SpaceX's Merlin LOX turbopump turbine. What do you mean turbopump well, I just probably shouldn't talk about SpaceX. Um, uh, let's see. Nuffly knows about the monopropellant test stand. Uh, Nuffly, sometime. I don't know. I'm working, and right now I'm working on something that I think is more important to society than a rocket engine. Um, but hopefully soon. I'm making steady progress on that. Uh, oh, that's fascinating. The microcontroller in this isn't available. That's not great. Although, I mean, replacing a microcontroller, that's, not the end of the world. There's a whole lot of microcontrollers out there these days. If they just like throw an STM32 on it, it seems like a fairly straightforward substitution. Yeah, so this is, I mean, this is good. This gave me a lot of insight into how they make this. It's also really cool. Like, check this out. They have a hole through the board for the fan. That's kind of awesome. Um, Operating and storage range. They got their address on it. Um, yeah, I mean, this was super informative. I really learned a lot from this. Um, I don't know how much of this is applicable. I see now that like more pressure sensing is a requirement. My ventilator design only has a single BMP 280 on a single line that splits at the machine, not at the patient, um, which seems to not be best practice from the medical industry. So that probably needs to be considered. Um, yeah, I don't know. I think that's about sorting it though. Does anyone else have any other things they think I should take a look at before I call it for this? Sleeve dog, aluminum bronze is not a particularly useful material for me in a rocket part. It's a relatively low temperature metal that's less thermally conductive than aluminum. Uh, it's just not a super great material for me. Yeah, Nathan, software bugs are going to be an issue, but I mean, I think the way to look at these emergency ventilators is that the patients that are going to be using them are dead if they don't have a ventilator. Um, and anything you do that makes that not happen is an improvement, right? Like when the outcome is certain death, extraordinary measures are permissible. But I don't know for a fact. I think that kind of just depends on the on situation. Okay, folks, I think that about does it here. Um, this was super fascinating. It was kind of fun to reverse engineer a part on stream. Thank you all for your insight. It was super helpful. Nathan, especially, that was came in clutch with some great tips on places to look. Um, I don't know. I may or may not keep plugging away at my ventilator design. It's the level of complexity here is very high, and I'm not sure how much of this is necessary complexity and how much of this is nice to have complexity. Um, Jay Hines, I really have to say you need to stop talking about SpaceX hardware. Um, uh, if that is what you're talking about, it's there are NDAs and I know the SpaceX InfoSec people and they're a really humorless bunch. Um, okay, so yeah, that will be where I end it. Thank you all for coming and watching. It was a ton of fun, and I hope you all are staying healthy and safe, and you are finding ways to get things done and improve yourselves, and as we all kind of get through this troublesome time. We just need a little perseverance. Uh, and with that in mind, hopefully that Mars rover happens soon. So thank you all, and have a wonderful evening.